All right, this lesson, 2.4, should hopefully feel like a little bit of a review. It's applications basically of using SOHCAHTOA in right triangles and some story problems here. So a couple edits here. This should say what angle is the right angle. We're told that we have a right triangle ABC and angle A is 34 degrees and little c, which would be one of our side lengths, is 12.7 inches. It should tell you what angle is the right angle. And in both cases, we're going to say angle C is the right angle. So the first thing I'm going to do is draw my triangle. So angle C is the right angle. We'll put A up top, I suppose. So the side lengths, we call the side across from angle A little a, and the side across from C is C, and the side across from B is B, little b. So I know that angle A is 34 degrees, and I know that C is 12.7. So I have to find angle B and side lengths A and B, and we are going to use what we know about SOHCAHTOA to do that. So first of all, measure of angle B is just going to be 180 minus 90 minus 34, which gives us 56 degrees. So that's done. But let's find A. Let's find side length A. So I'm going to use the measure of angle A that I know, and A is the opposite leg of angle A, and C, which is the one side length I do know, is the hypotenuse. So opposite and hypotenuse means I'm going to use sine. Sine 34 equals A over 12.7. Which means I'm going to multiply both sides by 12.7. So A is going to be 12.7 times sine 34. And that's what I'm going to type into my calculator right there, which means A is 7.102. Remember, we're getting in the habit of rounding to 3 decimal places. Last thing I need to find is side length B, and B is the adjacent leg. Oh, cosine 34, sorry, not cosine B, equals adjacent over hypotenuse. So similarly, I'm going to do 12.7 times cosine 34, which means that B is 10.529. All right, I would like you to pause the video and try to do example 2 on your own. So pause the video, give it a try, and check back when you're done to see how you did. All right, there are lots of ways that you could have gone about finding the missing elements of this triangle. But what I did is I used the Pythagorean theorem to find the side length that we were missing. And I got 45.552 from that. Then I set up this equation. Sine A equals 29 over 54, opposite over hypotenuse. And then I used inverse sine to find that the measure of angle A was 32.482. I started setting up another equation to find angle B, and then I thought, wait a second, I can just do 180 minus 90 minus 32 to get that final angle measure, and I got 57.518. All right, Couple more examples here. Shelley knows that when she stands 123 feet from the base of a flagpole, the angle of elevation to the top of the flagpole is 27 degrees. Okay, angle of elevation or depression is always with the horizontal. Always with the horizontal. So this is the angle compared to if she's looking straight ahead of her versus her angle looking up. So here's Shelley. And if she's looking out, here's the flagpole. And then she's looking up to the top of the flagpole. This angle right here is the angle of elevation. And that is 27 degrees. Her eyes are 5.3 feet above the ground. Okay, so she's 5.3 feet tall. And we also know that she is 123 feet from the flagpole. And we want to find the height of the flagpole. Okay, so here's the thing. I have this triangle. And I know this distance here. I'm going to use what I know about SOHCAHTOA to find this length, and then I'm going to have to add 5.3 to account for the height of Shelley. So the equation I'm going to set up, x is my opposite leg, 123 is my adjacent leg, so I have tangent 27 equals x over 123. So I'm going to do 123 times tangent 27, which gives me 62.672. But then I have to add 5.3 to account for Shelley's height. So the flagpole is 67.972 feet tall. The length of the shadow of a building is 34.09 meters tall. Wow, okay, that's a confusing sentence. The length of the shadow of a building, 34.09 meters tall. So that's saying the building is 34 meters tall and the shadow is 37 meters long. Okay, so here's our building. Here's our shadow. And the sun is somewhere over here. So we have 34.09. The shadow is 37.62. And we want to know the angle of elevation. So that is this angle right here. Remember, the angle of elevation is always with the horizontal. So what do I have? I have the opposite leg and the adjacent leg. Tangent theta is 34.09 divided by 37.62. I'm going to do the inverse tangent. Inverse tangent of 34.09 divided by 37.62. Punch that all in one go. We get 42.182 degrees. All right, one last example. Francisco needs to know the height of a tree. From a given point on the ground, he finds that the angle of elevation to the top of the tree is 36.7 degrees. He then moves back 50 feet. From the second point, the angle of elevation to the top of the tree is 22.2 degrees. Find the height of the tree. Okay, this one is a little bit more involved here. So we have a tree. And when Francisco is standing at some point, the angle of elevation is 36.7 degrees. Then he moves back 50 feet, and the angle is now 22.2 degrees. So we really have two things that we don't know, which means we're going to have to set up two equations and treat it like a system of equations. So like I said, this one is a little bit more involved here. So I'm going to call this x, this distance, the first distance that Francisco's standing from. And we're going to call y the height of the tree. So I have two triangles really with two different variables. So what I know is that tangent of 36.7 equals y over x. And then the other thing is that tangent of 22.2 equals y over x plus 50. So, how are we going to solve this? Well, we are going to use substitution. And in fact, we are going to actually finish this problem together just because there's quite a few steps involved. This is like an extra challenge problem. If you're able to do these first four examples pretty comfortably, I would say you're in a pretty good spot. And we will finish working through this final example when you're back in class next time.